Hello and welcome to IFT 360. This is the final project video demonstration. My name is Jason Merritt and I'll be your presenter today. For this final project, I elected to expand upon the Module 3 pathfinding program. And in that module, originally we were using the breadth first and depth first search algorithms to find the path to a source city and a destination city. In my example of the code, or I guess my iteration of the code, I elected to implement Dijkstra's uniform cost search, and this algorithm will get us the truest, shortest path between the cities, and I will briefly explain how my code works in this video. So we'll jump right into it in the main Python function here. The first thing I implemented was I didn't like the original code and how the cities start and end were hard coded in. So I actually implemented a prompt for the user. So we can just, on the command line screen, we'll see enter your start city and enter your target city. So unlike, breadth first or depth first, that ignores the travel cost, the uniform cost is going to expand those paths between start and end and then do the total cost between the city, which will guarantee us the shortest path possible. So let's look at how this is done in Traverser, the graph traverser Python function. So I didn't modify the breadth first code, I just left it in there, but I worked down below and wrote my own uniform cost function. So with the function, first we kind of construct a graph, and then each city is a node and with an edge cost with a specific distance. So those weighted edges are what allow the Dijkstra's uniform search function to make the informed decision of where to go next. So in the function, we're going to use a distance table, we're going to use a dictionary, and we're going to use a parent table and a priority queue. The distance table is the one that's going to store the lowest known cost to each city. That parent table is going to be what helps to print out that final path between how it got there. And this will make a lot more sense, I think, once I demo it. And the priority queue is always going to select the next city with the lowest accumulated travel cost, because that's what we're really looking for here. And I did write in some buffers or safety nets. So if you would put in like the same start city and destination city, it's going to tell you your path is 0 and it's not going to do anything. Or if you put in a city that doesn't exist, it's going to tell you, well, that city's not on the graph, try again. So down here in my main loop, let me make sure I can get it on the screen here. The algorithm repeatedly just removes the cheapest node from that priority queue we talked about. And this is because the program now knows it's found the absolute cheapest path. So it's going to check all the neighboring cities, and for each one, it'll calculate the cost reaching that neighboring city through the current node city. And if that cost is cheaper than any previously known path, that distance table will be updated, and that neighbor city is pushed into the priority queue to be explored later. And this is the essential process that will get us the lowest cost. So let's go ahead and start putting this to use so I can show you what all this means. We'll do 3 examples, and the first one will just be our kind of error validation. Let's say I put in something that doesn't exist. I put in Arizona and I put in Charleston. This is where I attend Arizona from, or Arizona State from. So we have nothing in there, nothing in the graph. It won't even execute. Now, if I do correct start city, but I accidentally put the same start city, we're going to get 0 because going to Arad from Arad is a 0 cost. So the third test will actually be what I wrote and be much more easily understood by seeing. If I go from Arad, and let's just say I'm going to go to Petesti. So the function will output that it did successfully reach a target. I'm going to show you how we decided to get there with using Dijkstra's uniform cost search. And I will show you the total path cost. In this example, it's 317. And as always, I've got my time and date stamp when the assignment was run. And that's how the function works. So let's just do another example. We'll do Craiovia, hope I'm pronouncing that right, to Jovita. And same thing. Reach the target, how did I get there, and what was my final cost? And that is my final project, and I thank you for your time.